Welcome to today's lecture. We start with the concept of integration and our kind of goal. So integration is the topic in the way of how Lebesgue drafted the definition. And our goal is, let's say, what is the goal of all of this integration? You know that integral from 0 to 1 x squared. Well, we know what it is, yeah. So it's the substitution of 1/3 x third, and then the value becomes 1/3 here, yeah. So we know kind of that's what we know from high school, that we know how to integrate polynomials. We use dx here to denote the infinitesimal. So what we wish to know now is actually kind of learn this for a general measure that we have learned so far. So we want to learn what does it mean to say we have an integral for some measure mu, and we want to define this in a feasible manner, and we want to define it such that we look at this as a map. So we take a function and we map it to the integral. Now we define, think about as definite integrals. So we are integrating across the full space where f is defined. And what the properties are, what we wish to have is a monotonicity, which means that if f is less than g pointwise, so we would like to have integral of f less than the integral of g for this general measure mu. We would like to have linearity, which says that the integral of we take a pointwise linear combination of functions f and g. So what we wish to have is that this is integral of f times c plus then d times the integral of g. Yeah. These are the basic properties that the integral should satisfy. Then we would like to have somehow continuity. So we would like to have that if fn converges to f in some sense, let's say pointwise, yeah. So if fn at every point, the value of this function converges to the value of the limiting function, so then we would like to have that the integrals converge as well. And then what else? We would like to have the property that for mu being the Lebesgue measure, on the real line, we would like to have integral of f with respect to the Lebesgue measure now. So now we plug in Lebesgue in place of mu. We would like to have the property that this becomes the ordinary for reasonable or good functions f. And that means this is what I would call the usual high school integral. Yeah. This is what we want, and we want this to be true for a measure. So now let's think about that. We have some set S, we have some sigma algebra calligraphic S, and we have some measure mu. And we have, let's remember, this could be now an arbitrary set. This would be an arbitrary sigma algebra on that set, and mu would be an arbitrary measure on the sigma algebra. Okay. That's what's going to be our setting today. Eventually, when mu has total mass 1, we know that then mu is a probability measure, and then we enter to the realm of probability. But actually, the theory of integration is equally easy or equally hard for general measures and probability measures in the beginning. So now we assume that mu could also have infinite mass or any finite mass for the total set S. And in this setting, f will be a function from S to the real line, which is measurable in the sense that it is S and the Borel sigma algebra measurable. This is our kind of setting where we would like to define what this integral means here. Okay, let's then see what's the kind of roadmap for today. Our roadmap is that we will study the properties, especially the monotonicity and linearity, and we study the definition that Lebesgue came up with for this integration. And later, we speak about the continuity. This is a little bit more problematic. So continuity has some troubles, and we cannot hope to have continuity for everything in the world. So that's the kind of law, that's the nature of the things in mathematics and logic and yeah, in nature overall. So we will look at, okay, under what conditions we can have continuity here. And later we might have a bit of a study, what can we say about this extension property of the ordinary integrals. That will work actually really nicely. So maybe it's fair to say that it's fair to put a green box here. These are kind of things that will generalize nicely. The red is something that requires a little bit of attention. That's our roadmap. If we don't have questions, then we will start. Okay, let me actually describe the approach. The approach to start with is that we will focus on positivity. So let's define ms plus as the functions from the set S to the non-negative real numbers which are measurable, in this sense that there's the calligraphic S, and then in the image space there's the Borel sets of the real line. And then we define this type of space called little s here, and that's those measurable functions which are non-negative and satisfies that the range of f is finite. So we are looking at positive functions or non-negative functions which only take finitely many values. And what does this little s mean? M means measurable. M stands for measurable. S stands for simple. So as I maybe mentioned before, in my opinion, it's a bad name, but that's how people call them. Simple functions are functions which only take finitely many values. And the approach is that we define an integral for the simple functions first. So we are going to define what an integral means for simple functions, and then that's what we are going to denote according to the lecture notes with the square. So that square means kind of elementary or simple thing. So we are going to define the integral for f being simple, non-negative, and measurable function. Then we will prove monotonicity and linearity for this setting, and then we extend it to the arbitrary non-negative functions. So we extend it to the measurable and non-negative functions, and then let's emphasize that here the plus refers to kind of the definition of the integral for non-negative functions, and the square refers to the definition of the integral for simple functions. Afterwards, we will prove monotonicity and linearity for that concept as well. And third approach is then to say, okay, what is this integral for functions which take values in positive and negative values? Okay, so that's what we will discuss later on.